Hello there. Try and do this. This is by far, I guarantee you, the most elegant proof of the angle sum theorems that you'll ever see. Classic. I finally got tired of that color chooser dialog. It was driving me crazy. No keyboard support. So I made my own. It's better. I love it actually. It has keyboard support. And that wasn't easy. I had to use a trick. Okay, now what this is this is a right triangle. I used the program because I was having a hard time making one just by inspection, so I quickly hacked in a thing to make one, and so I'm going to try and draw a little square here. Let's say this color. Change modes. This is a right triangle that previously had this line hanging down. So its angle, let's say the blue line was initially lying this way, and I rotated the triangle through an arbitrary angle called A. All right. So there's nothing set up about this situation. I mean, A and B are both arbitrary. I've taken a right triangle with arbitrary angle B and rotated it through an arbitrary angle A, and then I've drawn a box around it. Okay? Now, what you can say about this picture here is that this angle is going to be A, has to be, right? Just what opposite angles are equal or something like that. It's very easy to show that this is the same as this. I want a slightly different color. I'm using those splines to try and make curvy things. So we know for sure this is A. Same as that angle. Oh, and this here I already put in as 1. So it was initially this was 1, and so it was a unit right triangle that can rotated through an arbitrary angle A. So what does that tell us? Well, that tells us that we know the length of this side. That's going to be cosine of arbitrary angle B. Okay, that's the length of this side, and the length of this here. Actually, let me color code that. That's fast to use this thing. With a good blue. And this here is a sign of B, right near the A there. You'll know by the color, because this is of length 1, that's cosine of this angle, and that's the sine of this angle B, which is arbitrary. And the fact that the fact that this is one is chosen arbitrarily. It's going to make you understand that there's nothing set up here. This is not a contrived scenario. It's 100% arbitrary. This is true for any two angles A and B. It didn't need to be a right triangle, but a right triangle is convenient. All right. Now, first off, this here length sine B is the hypotenuse of this triangle, right? So the cosine of this length and this angle A, right? Like sine B cos A is the length from here to here. You know, this cos this. So this length, I don't know if I should try. I can try. I'll try. I don't want to get too much of a mess. That's not too bad. You see how those splines are handy. So that's sine B times cos A. Turns out that has to be true because that's just a fact of life. And this here, this length, would be sine B sine A. Okay. Now, what about this length here? Let's use a different blue color. Light blue. The thing about the lines is that you can draw a natural looking shape, and they look okay. You know, I didn't buy a $200 electronic pencil to do that. Okay, what is this length? Well, the length of this hypotenuse is cosine B, right? And this would be the sine angle A for this hypotenuse. So this would be cos B times sine A. That's a good dot. What's our color? What is our color? Or blue for this? Darker. Right? Similarly, for the height here, which I'll do in yellow, I don't want any bit by mosquitoes. Don't give it much. This length here is the cosine of this height for this hypotenuse and this angle. So that's cos B, cos A. And that will be dark blue, I guess. Oh no, yellow. Yellow. Ah! Well, if I can get that back. Yeah, hang on a sec. Oh, I know. I'll try something anyway. That does it. I have two of each now. I lost my little sprite though. Oh, I deleted it. I wanted it in yellow. Cos B. Oh. Sorry, hang on, I have to pause. Sorry if the noise is too annoying, but what we got here? Cos B times cos A. Those mosquitoes can't fly in the wind. It's saving me. It's saving my life right now. Oh yeah. Now, the next thing to notice, and this is quite easy to show, is that what color was I using? Almost white. That this angle is A plus B. That should be in some kind of yellow, probably. Now, the way to see that is to notice that this here, this angle, not yellow, this one here is pi over 2 minus this whole angle is pi over 2, and we have b plus a plus this angle is pi over 2, so this angle is pi over 2 minus b plus a. Or a plus b, right? Probably yellow. And the sum of these two angles has to be pi over 2, so therefore this has to be cancel that one, so this is a plus b. Okay? Now since this length is 1, and this angle is a plus b, then this whole distance here is the sine of a plus b. I'm going to draw a thing. Try and make it less pronounced. Okay, so this whole, because this is unit length, and this angle is a plus b, then this here is the sine of a plus b. Plus epsilon. It's a rounding error when something is off by like, okay, let it go, by like 0.000000001, and you get an assert. Okay, so that means that sine of a plus b is the sum of these two terms. So you can write that result here. That's sine b cos a plus cos b sine a. Results color nor. Oh, that bugs me. Okay, so that's the first term already proved. Now we know this entire length is cos b cos a, and that's equal to this length plus sine b sine a. Well, this length here is the cosine of a plus b. Oh, come on. I'm going to get it on everyone. Make it longer. Doesn't really matter with these splines. I'm not going to finish it. This is cosine a plus b. Shut up. Okay, now, so therefore we have the second result already with the assertions. Shut up. Which is that this plus this equals that. So cosine a plus b is cos a cos b minus sine a sine b. You see that? My real marks or this. Shut up. For the fifth. Well, you'll have to open up, Okay, well it almost fits. Where does it read best? Over here. Okay, so those are the addition formulas, and all I had to do was take one triangle and rotate it a little bit from the normal that happened to be a right triangle, and just by comparing the sides we can see just by inspection that the angle sum formulas are correct, at least in this case. I don't know how you generalize this argument to obtuse angles, but I'm sure it wouldn't be difficult. Okay, well, I gotta shut this thing down and stop it from. Let me just hit retry. Let's see what the difference really is. Look at this, 9. Okay, and I've added. This is supposed to be the smallest possible number representable as a double. And because of this 9 here, it's not in between, right? It's a little bit more than 1.0. So I'll have to figure out how, like, just create a comparison operators for doubles or something, so that I don't have to, all the time have to say, plus or minus some amount. Okay, see ya.